Alright, in this video we'll be going through the 2020 Mechanics Exam. The way I recommend you watch this video is to pause the video before every question, try the question yourself. Once you've completed the question or get stuck, unpause the video to see how I go about getting the answer. Tom flies an average sized plane with a takeoff mass of 7.5 times 10 to the 4 kgs. There are times when he flies it horizontally in a straight line, and there are times when he has to take a circular path, such that the plane is banked at an angle to the horizontal. Draw the force due to gravity and the lift force on the plane in these two situations below. Okay, so in this first scenario, we would obviously have our weight force coming down like this, and our lift force would be equal and opposite, like so. So we can call this F lift, like that. Alright, so these two vectors should be equal length, okay? In our second scenario, we would again have the exact same weight force, so try to make these vectors the exact same size, and our lift force is going to come up like this. And in this case, oh, that should be lift, like that, okay? And in this case, our lift force should be much greater than our weight force. The reason for that is because the vertical component of our lift force, so we can call this F lift Y, so the component of our lift force in the vertical direction. Our vertical component of our lift force must be equal to our weight force. And the horizontal component of our lift force, so F lift X, right? F lift X, this is what provides our centripetal force that will allow the plane to go in a circle. Okay, so because the vertical component of the lift force must be equal to the weight force, but the lift force is also providing an FC, the vector of our lift force must be greater than our weight force, okay? Compare the size of the force due to gravity and the lift force on the plane when Tom flies it horizontally in a straight line and when he flies it in a horizontal circle banked at an angle. Well, I did not know this question was going to come up, but this explanation is essentially what I said in the previous question. In our first position, the weight force is going to be equal to our lift force, okay? And therefore, the forces are balanced, okay? So that's our first scenario. In our second scenario, our weight force remains the same, so same as our first scenario, okay? However, our lift force is greater than our first scenario, and this is because the vertical component of our lift force is equal to the weight force, and the horizontal component provides our centripetal force, okay? And in this case, the forces are not balanced, okay? We know the forces are not balanced because FC is a net force, okay? Our centripetal force is a net force. And so if there's a net force present, then the forces must not be balanced, all right? So pretty much the exact same thing that I explained in part A. On one occasion, Tom flies the plane with mass 7.5 times 10 to the 4 kgs in a circular path with a speed of 54 meters per second, banked at an angle of 35 degrees to the horizontal. Calculate the radius of the circle that the plane describes. So we would have our plane, okay, this is our plane, and we have our horizontal right here, and this is 35 degrees, like so, okay? And so as described before, we would have our weight force coming down, and we would have our lift force like so, F lift, and we know that the horizontal component of our lift force is going to be our FC, okay? So we can make a vector triangle of this. We have our lift force coming like this, our weight force coming down, and then our FC like so, okay? So this is our FC, this is our F lift, and this is our weight force, okay? And this is our angle 35 degrees. Alright, if you don't know how I got this angle of 35 degrees, I'm pretty sure I explained it in my horizontal circles video in my mechanics playlist, so you can go check that out, okay? But this is the angle 35 degrees, alright? So as described in the previous question, so as described before, the horizontal component of our lift force is equal to our FC, and the vertical component of our lift force is equal to our weight force, okay? So you can see here, we can replace this with F lift X, okay? And this is also equal to F lift Y, okay? And so as you can see from here, the vertical component of our lift force is equal to F lift cos 35 degrees, okay? And that's obviously equal to our weight force, okay? And so therefore, F lift cos 35 degrees is equal to mg. Same thing for our FC. We know our F lift horizontal component is equal to F lift sine 35 degrees, okay? And that's equal to FC. And so therefore F lift sine 35 degrees is equal to mv squared over r, all right? And so what we can do is we can do F lift sine 35 degrees all over F lift cos 35 degrees is equal to mv squared over r divided by mg. okay? Now as you can see here, our F lift cancels out, and we are left with sine 35 all over cos 35, and we should know from our math courses that sine theta all over cos theta is equal to tan theta, okay? And so this becomes tan 35 degrees is equal to mv squared over r all over mg. And so we can simplify this to tan 35 degrees is equal to mv squared all over mgr. And as you can see, these masses cancel out, and we get tan 35 degrees is equal to v squared all over gr. And remember, we're trying to find our radius, and so therefore we can say our radius is equal to v squared all over g tan 35 degrees, and therefore our radius is equal to 54 squared all over 9.81 tan 35 degrees. And this gives a radius of 424.51 meters, or 425 meters. There we go. Tom then flies his plane at a height of 1.28 times 10 to the 4 meters above the surface of Earth. Calculate the gravitational field strength at the height that Tom flies the plane. Okay, so for this question, we can assume that Tom's plane is a point mass, okay? And so what that means is we basically just assume all his mass is concentrated at a singular point. The reason why we can assume this is because if we were to think about the size of the Earth versus how small Tom's plane is, okay, the size of Tom's plane is a non-factor, okay? So if we have Tom's plane as a point mass and we have our Earth right here, okay, this is our Earth, okay? The center of mass of Earth is obviously going to be in the center, okay? And remember, when we have our equation, Fg is equal to gravitational constant, big mass, little mass, all over r squared. This r squared is the distance between the two center of masses of the objects, okay? So it's the distance from the center of mass of Earth to the center of mass of Tom's plane. So it's this distance right here, okay? So therefore, in the question, we are given how high Tom flies above Earth, so we're given this distance right here, and that is 1.28 times 10 to the 4 meters. However, that's obviously not the full distance. We need to take into consideration this distance right here, okay? And that is 6.37 times 10 to the 6 meters, okay? Now, we don't take into consideration the radius of Tom's plane because, again, it's a point mass, okay? So 1.28 times 10 to the 4 plus 6.37 times 10 to the 6 is our radius, okay? And that gives a value of 6382800 meters, okay? So now we can just simply plug in our numbers. Our gravitational constant is 6.67 times 10 to the negative 11 times the mass of the Earth, which is 5.98 times 10 to the 24, times the mass of Tom's plane, which is 7.5 times 10 to the 4, okay? All over our radius squared, which is 6382800 squared. Okay, this gives a force of 734,286.9478 newtons, okay? This is not the final answer, because as you can see, it asks to calculate the gravitational field strength, and that is just another way of saying the acceleration due to gravity, okay? So we know that our force is equal to ma, okay? And so therefore, if we want to find the acceleration due to gravity, our force is equal to mg. And so we can say that our mg is equal to 734,286.9478. Therefore, our g, which is our acceleration due to gravity, is equal to 734,286.9478 all over our mass, which in this case, our mass is 7.5 times 10 to the 4. This gives an acceleration due to gravity as 9.79 meters per second per second. Now, some of you keen-eyed individuals would have just said that Fg is equal to mg, and that's equal to g, big mass, little mass, all over r squared, and just cancelled out these m's, and we would have g, big mass, all over r squared, and that would give you 9.79 meters per second straight away, and you would be correct if you did that. So that's a little shortcut that you can do. Now, also, again, in the marking schedule, the unit they used was newtons per kg. I will just let you know that that is the exact same thing as saying meters per second, okay? The dimensions are exactly the same. If you want more on dimensional analysis, it's actually one of the first videos I made. I'm pretty sure it's in the scholarship physics playlist, okay? But these are dimensionally equivalent, okay? And I'll just quickly show you what I mean by that. We know that F is equal to ma, like I said previously, and the unit for force is newtons. the unit for mass is kg and the unit for acceleration is meters per second. And so we can say that a Newton is equivalent to kg meters per second, okay? And so if we plug this into here, we get kg meters per second all over kg, that's equal to meters per second. These kgs cancel out and we get meters per second is equal to meters per second, okay? So these are equivalent. So you could say G is equal to 9.79 newtons per kg. Same thing. All right. Sandra dives from a diving board that is 10 meters high. She finds that she can do somersaults, which are just rotations, by tucking her body in. In the tuck position, her body can be modeled as a sphere with mass 60 kgs and a radius of 0.2 meters. The rotational inertia of a sphere is given as I is equal to 2 over 5 mr squared. While in the tuck position, she rotates with a constant angular velocity of 9.56 radians per second. Show that her angular momentum is 9.18 kg meters squared per second. We know that our angular momentum is equal to I omega. I is given as 2 over 5 mr squared. We are given her mass and we are given her radius. And so we can simply plug in those numbers. 60 times 0.200 squared. And this gives a rotational inertia of 0.96 kg meters squared. Okay? And so therefore we can simply plug in this value into here. We are also given her angular velocity, so it's just a simple case of plugging in our numbers. And this gives an angular momentum of 9.1776, which is equal to 9.81 rounded to 2 dp, and that is kg meters squared per second. There we go. Just before entering the water, she straightens out her body, thereby changing her rotational inertia. Explain what effect this will have on her rotational motion. Comment on her angular velocity and rotational kinetic energy. You may ignore the effects of friction while she's in the air. Okay, so before she stretches out her body, she is tucked in, right? So therefore, in the before state, more of her mass is closer to her axis of rotation. Okay? And therefore her effective radius is decreased. Again, if you don't know what effective radius is, I go through it in my rotational motions video on my mechanics playlist, okay? But in the before state, her effective radius is smaller. When she stretches out her body, her effective radius will increase, okay? And therefore, as I is directly proportional to mr squared, if her effective radius increases, then her rotational inertia is going to increase. Okay? And therefore, as friction can be ignored, our angular momentum is conserved and therefore is constant, and we know our angular momentum is equal to I omega, and as how rotational inertia has increased, our angular velocity must decrease. Okay? Now, in terms of rotational kinetic energy, we know our rotational kinetic energy is equal to half I omega squared. Okay? Now, in this case, we have a situation where our rotational inertia increases, but our angular velocity has decreased, okay? So we have one value that increases and one that decreases. So what happens to our EK rho? Well, because angular velocity is squared, it's going to reduce more than our rotational inertia is going to increase. And so overall, there's going to be a net decrease. And so our rotational kinetic energy will decrease as well, okay? And so you can write that in. It takes Sandra 0.28 seconds to straighten out her body just before entering the water. Her rotational inertia becomes 4.8 kg meters squared. Calculate her angular deceleration during this time. Okay, so angular momentum is still conserved, and we know angular momentum is equal to I omega, okay? And so we can use this to calculate her final angular velocity, and so her final angular velocity is equal to L all over I. We found her angular momentum as up here, 9.1776. 9.1776 all over the rotational inertia, which we now know is 4.8, okay? And that gives a final angular velocity of 1.912 radians per second, okay? Right, we also know the kinematic where our omega finally is equal to our omega initially plus alpha t. And so therefore we want to rearrange for our angular acceleration. And so we get omega finally minus omega initially all over our time is equal to our angular deceleration. And so now as we have all our values, we can just simply plug them in. We found our omega finally, which was 1.912, minus our omega initially, which we found right here as 9.56. And that's all over time, which we are given right here. So 0.280. And this gives a angular deceleration of negative 27.31 radians per second. And again, it's negative because we're decelerating, right? One day, Sandra observed Tapu practicing somersaults from the diving board. Tapu does 2 complete somersaults in 1.25 seconds. Calculate Tapu's average angular velocity while executing the somersaults. So Tapu completes 2 complete somersaults, and so therefore the angle at which she rotates is equal to 2 times 2 pi, which is obviously equal to 4 pi. Okay, so that is the angle in which she rotates during this time. And we know that our omega is equal to theta all over our time period. And so that's equal to 4 pi all over 1.25. And that is equal to 10.05 radians per second. There we go. Serena sits on a rigid swing that is 3 meters long. Show that the period of the swing is 3.5 seconds. So we know the equation where our period is equal to 2 pi square root L over G, right? We are given all our values, so we can just simply plug that in. 2 pi square root our length, which is 3 meters, all over 9.81, okay? And this gives a period of 3.47, which is indeed roughly equal to 3.5 seconds. There we go. Explain, giving reasons, how the period of the swing will be affected if Serena stands up on the swing while it's swinging freely. So this question touches on an important topic. When we have a swing, or any pendulum for that matter, okay, let's use a pendulum in this example. When we use this length in this equation, what that length is saying is the length from the pivot all the way to the center of mass of this object, of the mass, okay? So when Serena is sitting down, the length is roughly like this length. Let's say her center mass is right here, okay? So it's that length right there. When she stands up, the center of mass is obviously still going to be roughly right here. And so as you can see, the length of the swing has effectively decreased, okay? And so when Serena stands up, her center of mass has shifted upwards, okay? And therefore that reduces the effective length of the swing. And therefore as t is equal to 2 pi square root L over G, as our length has decreased, and obviously G has not changed because that can't change, and obviously 2 pi is not changing, and so therefore our period will decrease, okay? The graph below is that of the restoring force F on Serena against Y, which is the horizontal displacement of Serena from her equilibrium position. Explain how the information in the graph shows that the swing is an example of simple harmonic motion. So we know the conditions of simple harmonic motion is that there must be a restoring force, and that restoring force must be proportional and opposite direction to the displacement. And as you can see, let's look at this graph. As you can see, when we're right here, the force is positive because the force is the y-axis. However, the displacement is negative, okay? So from there, we can see that the force is proportional to the displacement. However, it's in opposite directions. The force is positive over here, but the displacement is negative, okay? And this is obviously illustrated by the negative gradient of the graph, okay? So the negative gradient of the graph shows that the restoring force is opposite direction to the displacement, okay? So that's one way in which you can explain it. The other way in which you can explain it is you can say that A is equal to negative omega squared y, okay? And if we multiply both sides by m, we get ma is equal to negative omega squared my, okay? And obviously ma is equal to force, so we get negative omega squared my. Now, because m is a constant and positive scalar value, okay, this basically just means as the pendulum swings, the mass of Serena does not change, right? So it has no effect on this graph, and so you can explain it through that way as well, okay? Me personally, I prefer explaining it using the definition of simple harmonic motion and then referencing the graph, okay? But you can also explain it this way, completely valid. Serena swings from NA to NB with an amplitude of 1.5 meters and a period of 3.5 seconds. Using the reference circles below or otherwise, calculate the velocity of Serena and the swing when she reaches 0.5 meters from N to B. So we're starting from A, and we are 0.5 meters from B. So we're probably right over here-ish, and we can draw in our phasor like so. Okay, where this angle is theta, and this right here is 1.5 meters, okay? And if we were to draw a line up here, if this distance right here is 0.5 meters, okay, that means this distance right here is 1 meter, okay? Not the scale, but you get the idea. And obviously this distance right here is 1.5 meters, okay? So now we can just draw that right angle triangle out. We have like this, theta right here. This is 1 meter, this is 1.5 meters, okay? And so we can calculate our theta value. Theta is equal to inverse sine 1 all over 1.5. This gives a theta value of 0.73 radians, okay? Remember, always work in radians when you're using the reference circle. And therefore, as our omega is equal to 2 pi all over our period, we get 2 pi all over our period of 3.5, and we get 1.795 radians per second. Because we are starting from max displacement, we have our equation V is equal to A omega cos omega t, right? And remember, as theta is equal to omega t, we can simply replace omega t with our theta, okay? And we have our velocity is equal to our amplitude, which was 1.5, times our omega, which was 1.795, cos 0.37, and this gives a velocity of 2.007 meters per second. There we go. And remember, when you're calculating this, always use whole values. I wrote down the rounded version, but in my calculator, I use the whole values, okay? And also, if you want more of an explanation on reference circles, I have a reference circle video on my mechanics playlist as well, okay? And we are done.